In certain conditions, bacteria can grow by splitting in two in every 20 minutes. So how can we model this scenario? Well, let's start off with time zero, and this will be the 0 minute. And it doesn't really matter what number of bacteria we start off with. We can't start off with zero, of course, because that won't grow. Let's just start off with one to make it simple on ourselves. So we have one bacteria at time zero. Then after 20 minutes, we have our first interval of time. So this will be time one, right? They split in two, so there's going to be two bacteria. Then we're going to do another jump by 20 minutes, and you're going to see that it's going to split again, but each one splits, and so each one splits in two, so it's going to be 2 times 2, 4 bacteria now. And as you can see the pattern growing, this is going to be 8 for the next time jump, and then finally 16 for the last one here. So what I have here is I've got a situation that I can graph by using time as my independent variable. That's going to be the horizontal axis. That's going to be time of 0. There's going to be 1 bacteria. Then at time of 1, we're going to have 2 bacteria. Time of 2, we're going to have 4 bacteria. 3, we're going to have 8. 4, we're going to have 16. 5, we're going to have 32. 6, we're going to have 64, and so on. And I've graphed these things in the red dots here. And so I have three different kinds of expressions that I've graphed, and we're going to ask which one fits the data. Of course, the last one does, but what kinds of graphs are these? The first one here is linear, and if I graph this thing out, I believe it graphs to, first one is here, x plus 1, and it meets the first 2 points, but obviously it does not meet this third one, the 4th one, the 5th one, the 6th one. Okay, the next expression that I used here was x squared plus 1. Once again, it meets the first 2 points, but then it's actually a little bit higher, 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 and then it's distinctly lower. It's going to be lower from that point on. This last expression is the one that we want. It meets every single point exactly, and this is to the power of x. That's the expression. This is called an exponential function. Exponential functions are the function where we have a times b to the power of x. A and b are just some specified number, so some real number, and then x is going to be the variable that we have. Now, a is the y-intercept. In this case, right, we have a y-intercept of 1 here. That's the first value, 0, 1. So a would just be 1 for our scenario, which it was, right? 1 times 2 to the power of x. We're not allowing b to be less than or equal to 0, or b to equal 1. So if b is less than or equal to 0, then the function really doesn't quite show what you want. Between 0 and 1, it's fine. At 1, however, 1 to the power of any value, right? 1 to the power of 2, 1 to the power of 15, 1 to the power of 1,000. It's always 1. And so you get a flat line. It's not really exponential in nature. It's just a flat line. So it really doesn't help us define the behavior. If also you have b less than 0, you're going to end up getting kind of this weird behavior where it jumps around a lot. I recommend trying it out on yourself, and you'll see kind of why we don't like that for what we're looking for. It's important to note that this is not the same thing as a polynomial function, right? Polynomial functions are something like this, where you have x squared, but exponential functions are 2 to the power of x. The x variable is in a different part of the expression. One's in the base, as in the polynomials, and one's in the power for exponentials. Of course, this base, in this case 2 that we had shown above, the base will change the graph. It's really the thing that defines the graph. And it's important to note that b to the 0 equals 1, because anything to the 0 power is 1. And so you kind of expect, if a equals 1, you're always going to meet this y-intercept of 1, since b to the 0 equals 1. And all of these things pass the vertical line test. So they are indeed functions, as I've been calling them. So 2 to the power of x here is this red line. I can just turn these off. This is 2 to the power of x. This is the one that I showed you above. And then if we have instead 1/2 to the power of x, this is going to be between 0 and 1, right? You can see that it goes the other way. It drops down as we go left to right. This one goes upward as we go left to right. This one drops down. But they both have kind of the same behavior. If you were to just kind of flip it over this y equal to x, or sorry, this y-axis line, you can see that they have kind of the same shape. Now, instead of 2 to the x, let's look at 10 to the x. You can see that 10 to the x goes lower, faster on the left-hand side. On the right-hand side, it goes up faster. That's because 10 to the power of x grows faster, either in the negative, that would actually be decaying faster, or in the positive, growing faster. And of course, if you look at 1/10 to the power of x, has again the same kind of behavior as 10 to the x. It's just flipped across this y-axis. But now it's going downward as you go left to right. Okay, for all of these things, we have a domain of everything. It did go infinitely to the left and to the right. I'll just show them all back up. I can just keep going over to left and right. These things look like they just shoot upward and eventually don't go to leftward, but they do. It just takes a very long time. Like these over here are so high up that I have to zoom out really far to find them. But the blue and the purple graphs are on the left-hand side. And on the right-hand side, the same kind of behavior. Now the red and the orange graphs are higher. But they do continue on indefinitely. And what you know is they both continue on, all 4 of them continue on indefinitely upwards. So definitely all these things are included in the range. The question is, what's the limiting value on the bottom? And that's going to be important to note that these are what's called asymptotes. They asymptote to 0. You can't really see it here, but there is actually just a little bit of a difference. This is the x-axis, and this is the x to the power of 10 on the left-hand side. As I keep going to the left, it's getting closer and closer, but it never crosses it. The same thing happens on the right for both the blue and the purple. It gets really, really close to it, but never crosses it, which means that it never hits 0. That's the domain, and the range is 0 to infinity, but it never hits 0. So I'm going to use a parenthesis instead of a square bracket. And as you can see here, both 2 to the power of x and 10 to the power of x, as we go left to right, it goes upward and upward and upward. This is called exponential growth. And as we go, we have 1/2 and 1/10. As you go left to right here, these things are going down to 0. It goes from a higher value all the way down to 0 until it reaches 0. That's called exponential decay. And it's important to note, I'm just going to look at 1/2 here. 1/2 is the same thing as 2 to the power of -1. And I have a power to a power, so I can write it as 2 to the power of -x. -1 times x is -x. And so 2 to the power of -x is the exact same thing as 1/2 to the power of x. And this is typically how we like to write exponents, is with this negative power instead of the 1/2. And so 2 to the power of x is growth, and we tend to think of it as 2 to the -x is decay. A positive exponent is growth, a negative exponent is decay. Now, for basic exponential functions, all we really need is to have the same base on both sides of the equations. If the base is the same on both sides, then the powers have to be the same. Okay, let's look at this one here. Now, when I look at this, I can see that I can make a base of 3 on both sides, because I know 9 is the same thing as 3 squared. And this one, Well, the cube root of 3 is the same thing as 3 to the 1/3 power. And we have a reciprocal here, so I can flip it by giving it a negative exponent. So 3 to the negative 1/3. And I like this because now I have 3 on both sides as a base. I need to make this just 3 here. Power to a power is multiplying the powers. And now you can see that I have 3 on both sides. The only way this is equal is if the powers are equal. 2x must equal negative 1/3. Divide by 2. And I get x equal to negative 1/6. Okay, for this next one, that 625 is the same thing as 5 to the power of 4. And 125 is 5 to the power of 3. And this is nice because now I have a base 5 on each side. So on the right-hand side, I'm multiplying like bases. I can do this by adding the exponents together. And then I have 5 to the power of 3. Once again, I have the same base on both sides. That means the powers must be equal. Okay, combine like terms. Subtract 7. And then divide by 3. Of course, you can always check your answer by just plugging this thing back into the top equation here. Same thing with this one. Plug it back into there, and you'll get the same answer. Go ahead and give it a try in number 1. Now, let's say we want to invest $5,000 in a retirement fund. If we got 10% as an interest rate on average, and it's compounded quarterly, how much will we have after 30 years and after 50 years? To do this problem, we need to have an equation or formula. And the basic compounding interest formula is A equals P to the 1 minus R over N. This is 1 plus R over N to the NT. And so all I have to do now is plug in the appropriate numbers into each one. So A is the amount after time t. P is the principal, and P is the starting amount. So the principal is going to be $5,000. R is the interest rate, not as a percentage, of course, as a decimal. So R is going to be 0.1. And N is how often it compounds per the time unit. And of course, the time unit is going to be years here. So if we're compounding quarterly, that's going to be a quarter of a year. In other words, N is 4 because it compounds 4 times per year. Of course, T changes, 30 and 50. That's what I have written here. All I have to do now is just plug it in and calculate. So A equals, P is 5,000, 1 plus R over N to the power of N times T. The first one is going to be 30, and then the second one is going to be 50. Okay. Really, a calculator is going to help you out a lot in this. It's going to be 1.025 to the 120, and then to the 200. And now I'm just going to plug this whole thing into the calculator. Gives me 96790.75. It's a dollar amount, so I'm going to run it to 2 places. And the next one is 697,819.47. Interestingly enough, what you can see here is that for the first 30 years, it takes the $5,000 to grow to about 100,000. But after that 30 years, now we've gained an additional 600,000 past that. And that's really the power of compounding interest. The idea is that as you're gaining interest, right? You're gaining each time it compounds, you're adding on a number. So after the first time it compounds, so after the first quarter year, you no longer have $5,000 in there. You have 5,000 plus, you know, whatever the first compound is. So it's going to be a little bit more than 5,000. And the next time it compounds, it's not compounded on 5,000. It's compounding on the bigger, bigger than $5,000 number. So as you keep going, you're compounding on more and more money, and it really shines in the long run. Okay, now, which account accrues more money after 30 years, compounding quarterly or daily? So quarterly, of course, is n equal to 4. This one we already found, so compounding quarterly was 96,790 and 75 cents. And then daily is going to be, we could just use n equal to 365 or 364. It doesn't really matter. So daily is going to be 5,000 times 1 plus 0.10 over 365 to the power of 365 times 30, since we're looking at 30 years here. Okay, so plugging the whole thing in gives me 100,386.443. So it was not that much more money, just looking at these two things. Of course, this is, this is what, about $4,000. That's a significant amount of money. But after 30 years, it doesn't seem to be that much money compared to the whole thing. However, all that's changed is how often our account compounded. We had the same time, 30 years, the same rate, 10%, but we got more money out of it. So that tells us that how often do we want our account to compound? Well, we want it as much as possible, because we just get more and more money for it. So then that means, well, what's the most that you can compound? Well, at 365, right? You can compound more, maybe 1,000, 1,000,000, 1,000,000,000. Really what you're looking at is what happens when n goes to infinity, when it's the biggest number it could possibly be. How often does it compound? Well, to talk about that, we must understand Euler's number. So just really quickly, the reason why you get more money is because effectively what you're doing is you're increasing how often or how long you're doing it for, how long you're leaving your money in there for, with a smaller rate. That's what the compounding effectively does, is it increases our years but with a smaller rate. However, exponential functions grow faster and faster in the long run, so you always want to compound more often. And as n goes to infinity, we need to know what this number is here. This is Euler's number, just about 2.72. It's an irrational number, just like pi, and it's named after Leonhard Euler, who was a very famous mathematician in the 1700s. But the discovery is accredited to Jacob Bernoulli, also a famous mathematician in the 1600s. As we let n go to infinity, this formula here that I've shown before, n goes to infinity, n goes to infinity. Of course, that doesn't really make sense for this because we can't plug infinity in. It actually becomes this formula. And I'm not going to prove why that's the case, but it does go to this formula. And this is called continuously compounding. Okay, if we have a continuously compounding interest, situation, how much money would be in the account after 50 years? So we have the same principle, the same rate, and now we're looking at 50 years. So previously, when we did that, we saw we had just about $700,000 after 50 years, compounding 4 times a year. Here, we do not use this previous formula that we've been using. We have to use this one because we don't know what n is, or actually n is an infinite, and we cannot plug infinity into a formula. That's where this new formula comes into play. We don't need to know what n is, or we don't need to plug in n, because our formula allows us to use e instead. Times 50. E is just a button on the calculator, just like pi is. So typing that in, it's going to give us $742,065.80. So by continuously compounding, instead of it was compounding, I believe, 4 times a year, that was just about $697,000 that we found previously. We got an extra just about $45,000, and all that happened was it compounded more often. Now, here's some other interesting formulas with exponentials. This is compound interest with deposits. You can see it's a much more complicated formula. That's the reason why I didn't go into it. But this portion is just the same compound interest formula. And this portion here is if you add a deposit in after all the compounding. So you're adding more money in, for instance, like a monthly retirement fund that you keep adding more money into it. This is actually going to grow more and more and more. So the 5,000 may not have seemed like it grew all that much after 50 years, which to me that's pretty significant. But if you add in these extra deposits, then this will actually grow to be much, much higher, because now you're compounding on more and more money. So that's typically what you would do for retirement fund. We can also model inflation using an exponential function using this here. So today's dollar value C with inflation rate R after T years. So what this is telling us isn't that our money has become more valuable, because it's going to be a bigger number with inflation. It means that, for instance, $50,000. So for instance, if I had $50,000 and whatever I plugged it into there, and it gave me as an output $200,000, that doesn't mean that I've increased my dollar value by $150,000. That means that $50,000 can buy the same as $200,000 after a certain period of time. It's actually a devaluing of money. Your money becomes less powerful. It can buy less things. Give it a try in numbers 2 and 3. Now, of course, these formulas have many more applications than just money. Money is a nice one to look at since everyone deals with it, but there's a lot more applications for it, and namely population growth. We started with bacteria growth, which is a population growth. And now let's look at a fox population. If it has a growth rate of 9%, and typically population will be compounded continuously because of the way, there's so many people that it's more reasonable to assume it compounds continuously than over a certain, daily or whatever like that. So in the year 2012, there were 23,900 foxes, and should say foxes. They were counted in the area. And what is the fox population predicted to be in the year 2020? So we have a growth rate of 9%. So R equals 0.09. And the year 2012 is our starting year. So think of this as year 0. This is like t equals to 0. And we have a starting population, or our principal, think of principal as the starting amount, really, of 23,900. Now, what's the fox population predicted to be in the year 2020? So this is, of course, if all the situation happens exactly the same thing as it is currently, well, in the year 2020, I should say, or sorry, 2012. If everything is the same, what would it be in 2020? Well, we're not calculating 2020 being the new year. It's really 8 years after the initial year. So we're wondering what happens when t equals 8. Well, it's compounding continuously. We can use the formula. We have our starting amount, 23,900, times e to the rate, times the time, and time is going to be in years. Well, let's go ahead and plug this into our calculator, see what we get. We get just about 49,101 foxes. So quite a bit. We've more than doubled our growth in those 8 years. Of course, this is only the case if everything's exactly the same, which might not be very reasonable, but that's what we have here. Give it a try in number 4.